PhD student at Purdue University studying under Dr. Berkay Chelik. And today I'll be presenting DRIVETRUTH, Automated Autonomous Driving Dataset Generation for Security Applications. This work was done in collaboration with Yan Mao Man and Dr. Ming Lee at the University of Arizona, as well as Dr. Ryan Gerdes at Virginia Tech. So, why are datasets needed for autonomous vehicles in the first place? Datasets are needed to evaluate correctness, safety, and security of autonomous vehicles. So you need a baseline correct dataset in order to verify whether or not your given proposed system is working correctly. So for example, if you have an object detector, you would need a 2D bounding box dataset for ground truth. You would run your object detector on this dataset, and then you would compare it with the actual results that you know are true, and you would see, how well am I doing. However, it is difficult to collect dataset in the real world under different varying environmental conditions, such as weather, location, and traffic. For example, for whatever reason, your data needs rainy weather. You can't just push a button and make it rain outside. And then you have the problem of accurately labeling data once you've collected it. So if you just have hours of raw video footage, it can be difficult to know what is the actual correct results that you need for whatever application you have it for. So for example, one way to do it would be to use a machine learning algorithm to automatically label your data. That comes at the cost of accuracy. Currently, machine learning algorithms average 60 to 70%, say, for object detectors in accuracy, depending on your application. So you're not going to get a 100% correct result if you do this. The other way you can do it is to manually label your data sets. So you have actual people look at the data, label pixel by pixel or object by object. But of course, this is time and labor intensive. So we have autonomous driving simulators, and autonomous driving simulators kind of lessen the workload of having to go out and collect data. They allow you to use different environments and control traffic, things like that. They're already being used for the development of autonomous driving. For example, Baidu's Apollo. And the reason why this works is that physics simulation and graphical fidelity has become so realistic now with simulators. I've included 2 screenshots of the Carla simulator, which our system DRIVETRUTH is built on. And you can see that they have, they look very realistic. And in actuality, machine learning algorithms have similar performance when trained on simulated and real data. So there have been previous autonomous vehicle datasets before, and we compare them with DRIVETRUTH, what DRIVETRUTH can do. So DRIVETRUTH, the beauty of it is has everything that previous datasets had. It has the 2D bounding box, 3D bounding box, LiDAR, but there are some extra things that it has. So for example, in addition to having the position and trajectory of the collector vehicle, it also stores the control information that you would get from the CAN bus. So the throttle, the braking, the steer value, you can tell how much gas somebody's putting, whether they're turning the wheel, and this actually provides the intent of the vehicle much better than you have trajectory. For example, if the wheel's being pulled left, that the car or the driver wants to turn left. Maybe the trajectory hasn't caught up, right? Maybe the car still pointed straight or isn't moving, but the wheel's gone left. You know now that the car is moving left. So that's something that's good to have. The other extra thing that it has is that it can do accurate ground truth with automated labels. Because we are leveraging a simulator in order to collect data, and we have some tricks that we can do that I'll explain later, we can get accurate ground truth because we know that this is the actual value being contained in the simulation. We can get that automatically and accurately without having to resort to machine learning algorithms and sacrificing accuracy. So a little bit of a deeper dive into what DRIVETRUTH actually is. DRIVETRUTH is an automated autonomous driving data collection framework built for the Carla simulator. It automatically labels 2D and or 3D bounding boxes with perfect accuracy since we're pulling from the simulation. But even for objects that don't have built-in bounding boxes or even mesh information that you can extrapolate from, such as the traffic signs, the trees, extrapolation is supported for those objects. DRIVETRUTH can determine what their bounding boxes would be using semantic raycasts. In addition to bounding box data, LiDAR output is supported if that is something that one desires. And DRIVETRUTH will collect the context information in the scene. So that includes the ego vehicle position, the heading, the velocity. It includes the ego vehicle's control info that we talked about, the throttle, the brake, the steer. And it also includes the internal ID, the relative velocity, the location, the rotation, and the distance from the ego vehicle for all objects. So the idea with the DRIVETRUTH generated datasets is that no matter your application, no matter what you want to do with the data, you can almost reconstruct the entire scene from scratch in order to pull what kind of data you want for your specific application. Now, bounding dynamic objects. So fortunately for some objects, Carla provides the bounding boxes as part of their model. Getting their bounding box information and their position and size is simply a matter of pulling all of the bounding box models in the scene. You remove any of them that the camera can see or aren't of interest, and then you project it to 2D for 2D bounding box collection if you want. Now, dynamic objects, of course, can be defined by the user in Carla. So if you were to create a, say, plane object or bird object, something that would be moving, but you didn't add a bounding box to it for whatever reason, you can still extrapolate the bounding box using the static approach, which we'll cover next, over here. So it's going to extract 3D information using this semantic LiDAR or semantic raycast system. So it works sort of like a LiDAR. You have a bunch of points that you split out like a light beam. They're just points, raycasts, that go out and they hit objects, and it generates a point cloud like you see on the right here. And each of those points, unlike a LiDAR, which just has position and intensity, has the internal ID and the semantic tag. So for each object, you know that this belongs, say, to car 1, this belongs to car 2, and of course the semantic tag, meaning you know the class of each object. So this is a very important thing that you can now use to cluster points into 3D bounding boxes. How do we do that? First, we filter the point clouds for the semantic tags we desire to track. So let's say we already got all the car and pedestrian bounding boxes before, we just want traffic lights. So we will say, I only want my point cloud to be points that have the traffic light ID, as well as any other thing that you're going to be tracking. So we filter the point cloud by that. Now it's just a point cloud of the class we want. Now we can cluster the points by their internal ID. So we can say this is traffic light number 1, this is traffic light number 2. We start pulling them into their own point clouds, and we separate the point clouds by internal ID. So we have each object as its own point cloud. Then the problem transforms from just pulling the simulation state for the bounds of the object. Now we can extrapolate that by getting the minimum and maximum extent of each point cloud cluster. If I know, this goes from, 5 meters away to 6 meters away, then that's about 1 meter in length, and I can say that, this point cloud extends this. I can create a 3D bounding box for that point cloud, and I can return it. And in that way, we can still have accurate simulation state, 3D bounding boxes that can be transformed into 2D bounding boxes, what have you, position, size, without needing to add extra information to the simulator. DRIVETRUTH is a configurable data collection framework that automatically labels a wealth of autonomous driving data. The idea is that whatever application you have, you can use a DRIVETRUTH data set and you can tailor it to your needs. DRIVETRUTH leverages semantic raycasts to obtain location and size of any object, even those without built-in bounding boxes within the simulation. So regardless of whether or not this object you put a bounding box for it, whether or not a bounding box exists, you can always get accurate information for that object with using one of two methods. DRIVETRUTH can be used for security and safety testing within autonomous vehicles, and we have published the code for public use at the following URL. That's all I had. I will take questions now. Thank you for listening.